So we have a bonus ESR with us. He joined us very recently, so he's just mostly introducing himself and some previous work he has done. For joining, please.
Yeah. So hello, and also from my side, my name is Maximilian Hilger, and I am also working as ESR7. So there is some overlap with the work that Prashant did before. Majorly, I'm using a different kind of radar sensor, namely a rotating 2D radar sensor. Here we have two videos where we can see how this data looks like. The white points here are the radar data compared to LiDAR data that is given in colored. This video was taken in a test site of Volvo, and here we can see why this radar is so important. The LiDAR signal is obstructed by the dust that is produced by the other machine, while the radar still can penetrate through these disturbances. So it's a pretty exciting sensor in this dirty and harsh environments. I am also working on SLAM. I'm also working on SLAM, which stands for Simultaneous Localization and Mapping, which Prashant also introduced in his presentation. What I noticed so far in my previous work and in the state of the art that I catched up to in Eurogroup is that there is a common architecture that is prevalent in a lot of different publications. And this is that we start with filtering radar data, then do the odometry estimation, which gives us high-frequency pose estimates. And after that, we need to detect loop closures and do post-graph optimization to reach global consistency and higher accuracy estimation. I will quickly walk you through all of these processes. First of all, we start with radar filtering. The input that we have from these rotating radar sensors are these radar images that look like this, which are built by having ranges and the angle that is sensed. We want to produce point clouds that we can use in scan matching. It has several objectives, this filter. First of all, we want to reject some noise that is in the radar data, but also we want to downsample the scan to allow for real-time estimation in the rest of the pipeline. An important point here is that the noise in the radar data is partially depending on the environment. For example, if we are in an indoor environment, we will have more noise in the data as if we are in an outside environment. So it's important to do this accordingly. And also, like Prashant said, the standard approaches from the radar community are not working well for SLAM, so we need to find our own solutions. With the generated point cloud, we then can do odometry estimation. And also here we have to take some considerations. First of all, the radar sensors are rotating at a relatively low speed. So the sensor that is used here in Eurogroup is 4 Hertz. So we can undistort the scans, and this gives us a performance improvement of up to 30% depending on other parameters. Secondly, the points that we get out of the filter, it's still sometimes more than 10,000, and these points are pretty unstable. So we try to approximate these points by using some features that still retain the geometry of the scan while being easier to handle afterwards. An example is given here. These are oriented surface points. But for example, a different approach would be to use the normal distributions transform, which also retains the geometry of the scene. Then, when we use scan matching, we not only use 2 consecutive scans, but we use submaps that are constructed of several different scans to have a richer representation of the environment. We then also weight some correspondences here to have a greater influence in the registration process, which further improves our performance. Then the registration looks something like this, and by this we get the motion increment of the robot. Finally, we still didn't get rid of all of the outliers. So we need to use some robust estimation techniques such as M estimation or RANSAC to account for the last outliers that are remaining. Now, the odometry produces a high-frequency state estimate, but it has problems with drift that accumulates through the time. So we have to detect loop closure, which means that the robot has to detect that it is at a position that he has previously visited. What comes in handy here is that the radar data with the intensity is material dependent. So we have implicitly some information about the environment in the radar scan, which is useful in descriptors that can be used to classify two positions or scans if they are taken at the same position. And an example of this is given here. This is the radar scan context descriptor, which also uses a polar representation of radar scans and is used in many pipelines that are used in radar SLAM. Finally, with the loop closures and the odometry estimates, we then built a so-called pose graph. Pose graph consists of nodes and edges, where the nodes are poses of the robot and its corresponding scans, and the edges represent transformations between different scans. And when the robot moves through the environment, it builds more and more of these scans and edges until we have the first loop closures. Then the robot detects a new transformation estimate between the nodes, and we can then optimize the whole pose graph, which moves the previous poses and gives a new estimate of the trajectory and the map. And this also rejects some of the drift that has accumulated in between and leads to globally consistent estimation. I also want to show a video. This was also recorded at this Volvo test site. And here we can see the odometry in action. Now the robot is traversing through its environment and it's recording data. And in a few moments, we will see that the robot revisits a location that it has visited before. And then you will see, first of all, that the drift that has accumulated, it's not that much. It's about 3 or 4 meters. We will come to this in a short moment. Yeah, here we are. And these green lines, these are the loop closure that the robot sees. So it is able to really well see the regions that it has visited before. Okay, this takes some more time, so I will continue. So what are the open challenges that I maybe want to tackle within my PhD? There are many different directions that we can get into. First of all, the data that we used so far was mainly produced in the context of autonomous driving, but we also want to generalize to other kinds of environment, for example, indoor environments or construction sites. Another thing is that there are a lot of new sensors emerging. For example, the 4D radar that Prashant's has been using, but also 3D spinning radar. And there is not only hardware-wise a lot of progress, but also in the signal processing internally in the sensor. And there's a lot going on at this moment, so we want to keep up with the technology. And finally, we want also to use information beyond geometry. That means, for example, the Doppler information that we can use from the sensors, but also the intensity data that we maybe can use, for example, for material object classification, which would give a whole new semantic interpretation of the environment that we have. Yeah, so this was my short presentation.